All right. This is the last Physics 214 lecture of the summer. I think we've done it. I'm very happy. This behind me is the worst Elmo I've ever worked on. Please forgive me for the quality of this. Look at this. This is horrible. But we're going to do it. You've got the video. The other source is the 214 final review from May. That's spring final. That should be good enough in addition to this. This will be online in a couple hours. So let's get started. And I gotta contort my hand. Plus, from this view, I can't see the screen. I practically am turned away from the audience, blah, blah, blah. Pity me. All right, now, what we're gonna do is first talk about the final. There's gonna be 50 multiple choice on this test. What? What was that? Someone upset me. 50 multiple choice. What I'm going to do is I'm going to pull from the multiple choice test banks for tests 1, 2, and 3, and then just put a third of them each into the multiple choice. Yes?
So it'll come from the whole thing, not just from what we had.
You know what? That's a good idea. Probably what I'll end up doing is, because in the end, you're going to go from effectively 25 per test to about 16 to 18. So I'll pull 7 of them out. And yeah, I don't see why not. I'm very flexible in my last day of work. So that's what we'll do. So just take a look at those multiple choice that you got on the test. The thing that's going to be a little bit tricky is to get the test 3 multiple choice from yesterday into that test, because basically I did a copy hatchet job. So I may have to do it again for just that test, and then the other ones we'll just do normally. There will be 2 appetizers, and really what I'm doing is I'm going over the stuff. I posted last night a sheet on what's on the final. The appetizers are kind of going to be wild cards. I don't know what they're going to be. I'm going to write it this afternoon. And what you want to do is you want to look at the problem sets, look at the problem sets, look at the tests, and look at those appetizers. Not the right-hand rule game. You will have to know it, but not necessarily for in terms of the game, which is just free points if you know how to do it. The 6 problems now. Metaphysical certainty. E-field vector addition. It will be on the test. So what I've done, people watching this, you could freeze it. I'll make a better version of this later. But this is the solution sheet that I used for test 1. And so what's happening now, don't bother writing this down right now. But what you can do later on the video is freeze frame it and then take a look. And so this is what we're going to do during this 2 hours. We're going to also we're going to do another of these problems. And what I'll try to do, if I have time this afternoon, is I'll rewrite it so that it looks a lot more pretty. But at the very least, you can kind of see what was going on. So the E-field vector addition, you're not leaving Eschenberg physics unless you can add vectors well. The next thing is circuit analysis. What I've done is I've looked at what were the big mistakes that the class had, big misunderstandings. And if you did really great on a problem, I'm not going to have it on the final, but for test one, those were the big two. Those are the big two that tripped over a lot of people, particularly V sub A, finding the potential at a particular point in the circuit. There is a lecture where I posted, or I threw the sheet on the display table showing how the equations broke down and how to find it. And we can go over one like that again. Another certain one is magnetic induction. With the bar that's moving. I can't promise it's going to go to the right, but it's going to go left or right, and then you got to do stuff. So understand the derivations behind all of that. Get to the point where you can get to that core equation, and then you can solve for anything you want. There is another. Oh. Compound lens. You're going to have a convex and you're going to have a concave lens. You're going to have them together, figure out where the final image is, describe it, all that fun jazz. For 5 and 6, now that we've looked at this, these two are test 1, that's test 2, that's test 3. So one is going to be a test 2 and the other one is going to be a test 3. So the ones from test 2 can be like particle spectrometer. You can do maybe even coupled with a velocity selector. B field addition. Stuff where you've got to know Q, V cross B, and ILB. So basically force on a wire, charge moving through a magnetic field, that kind of stuff. And that would be good, very good test 2 material. Would I do another Kirchhoff's laws? I don't think so. What, you want to do Kirchhoff's law? See, yeah, and a lot of people got that right, but then a lot of people got it wrong. I don't know. I'll decide later, but Kirchhoff's law. That could be, but the problem is, here's my problem. I've got 4 of the 6 problems locked in already. If I use Kirchhoff's law as one of these, then that kind of, it restricts me from using any more material. And we've already got a circuit problem on it. I don't know yet. This is something where it's like, if you have questions this afternoon that require like 30-second answers, or you have scores that need to be recorded for homework, come in. But if you want to sit down for 3 hours and talk about Kirchhoff's laws, I'm not going to do it because there's just no time. I got to write this thing. Test 3. What I'm thinking is something weird with like lens mirror. And when I'm thinking lens mirror, I'm seeing into the future. And something, I've been kicking around ideas of doing appetizers with a lens or a mirror. They're very easy to do. You got an object, you got a lens or a mirror, give me the image, give me the magnification, bam, 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 in and out. That's a good appetizer problem. Not asking for ray diagrams, just something. Thin films, single slit, double slit. Single slit looks better than double slit because we've already done a double slit, but I don't know. So I would just be ready for both, and it's not that big of a deal. And so that's kind of the test, kind of the final. What I've done also, if you haven't been on Blackboard in a while, the finals have been posted, and what I'm going to do, since, I mean, granted, we got an hour and a half, but that's still hour and a half. We'd be wasting a lot of time with the multiple choice. So what I'm going to do is I'm going to take these finals and take the solutions and post them so that you guys can take a look at it. One thing that we do have to do, it's a small inconvenience. There are a few people who, most of you have experienced this rant before. I gotta do it right now, otherwise the people who have never taken my course before won't know. I really spend a lot of time trying to get the grades right. And so when we take the final in Lamar tomorrow, you'll have an hour after the final to make sure that you're not making a mistake. And all I want from you is, after the final through Monday, don't bother. Don't come by my office. Don't wade into my office from Martindale. If you do that, if I catch you, if I see you, if I sense you, I will take 200 points off your final. Does that mean you can get a negative score? Yes. Yes, you can get a negative score from this. So what this does is it prevents students from continuously coming by my office and going, Dr. Eschenberg, I tried real hard. Dr. Eschenberg, is there any extra credit that I can do? Let's not talk about the extra credit that you can do. Let's talk about the credit that you didn't do, resulting in you needing extra credit. So don't, and oddly enough, that sound is the same sound that your GPA makes when it's dying. So I don't want to hear that sound. It's basically because I need time to meditate and get it right. Trust me, I'm out of here. I'm bouncing. The last thing I want is to be bothered and disturbed. I'm going to make every effort to make sure you got the maximum score. I'm going to post the grade for the final, put the finals in a box, give it to Daniel, and then boom, I'm turning into professional too. So that's it. Just don't bother. Now, you're free to drop by today. Once I've got the finals printed tomorrow morning, if you see me, and I'm not completely angry, but that means I'm done with the final, and you can come in the final. But if I'm writing the final, then please don't. That's it. So what I'm gonna do is really whatever you guys want me to do for the next whatever. Requests? Yes, in the back. Compound lens, okay. In fact, what we'll do, I think, will be good. This is the yes. Yes. In fact, Scantrons are graded. The grader is a little bit slow. He told me he did have it before class, but he didn't, which I'm fine with that. Don't be angry at this fact because he's a different grader than the one that's been handling your test 1 and 2, and he's a lot better, in my opinion. The plan is, hopefully, knock on wood, that when I walk over there, the tests will be there. If the tests are there, it's only going to take me an hour to get them paired up with the Scantron, added, recorded, and then my estimate is if they're there already, if they're there by noon, I'll be done by 2. The grades will be posted by 2, and then you guys can talk about it. And then they'll definitely be outside my office, so you can come by and pick them up. But that's a good question. All right. This comes from the summer of 2016 final, and you have this. So let's just read it out. Object is 30 centimeters left of a 20 centimeter convex lens. To the 51 centimeters to the right, that's an odd number. You've got a concave lens of a negative 15 centimeter focal length. I gotta know where it is. I wanna know total magnification, describe it. This is a classic compound lens. You do this in 2 stages. The first thing you do is you understand that 1 over F1 plus or equals 1 over O1 plus 1 over I1. God, I hate the angle of this. This means that 1 over F1 minus 1 over O1 is equal to 1 over I1. So I1 is equal to 1 over F1 minus 1 over O1. I get this. So this makes it 1 over 20 minus 1 over 30 inverted, which should give me, I want to say 40, but let's find out. No, it gives me 60. So that is the image 1 distance. The magnification of this negative 60 over object distance, which is 30, negative 2. Pen's not dying. So that's the distance. It's 60 centimeters. It's 60 centimeters from here, which means it is 9 centimeters to the right of the concave lens. So it's 60 minus 51, or 9. That 9 centimeters is to the right of the concave lens, which means that O2 is equal to negative 9. This is the only case that we deal with in 214 where the object distance is going to be negative. It's never a primary object distance. It's the O2s, which on occasion are negative. And so we put that into this type of equation. I2 is equal to 1 over F2 minus 1 over O2 inverted. negative 15, negative 9, and I get Elmo. This Elmo is horrible. I get positive 22.5 centimeters. So the image, the final image, I2, is, I'm looking for the final image with respect to the convex lens. So this distance is 51 plus 22.5, which gives me 73.5 centimeters away. So that's the distance that from the convex lens. M2 is negative I2 over O2. That gives me minus 22.5 over negative 9. So this is positive 2.5. Now, because it is to the way right of the concave, it is real and right. This magnification is positive 2.5, but the total magnification, M, which is M1 times M2, is negative 2 times 2.5, or negative 5. So because the magnification is negative 5, the total magnification, it has been inverted, and it is enlarged. And so that is a compound lens problem.
That's kind of the magnification. Is that with respect to the original object?
Yes. So if you had a 10 centimeter tall object on the left, the final image on the right would be 50 centimeters and inverted. And just as you guys have heard this before, there will be no ray tracing for this thing. In fact, there will be no ray tracing on the test at all. Yes? I could make it virtual, but that's dumb. In terms of where do we, hidden in the corner. What's the compound lens used for? We use it in lab. It would be kind of dumb to have compound lenses set up so it could happen, but you know me, I like to have problems that have lab consequence or lab expectation. Yeah. So this most likely is going to be real. Like, someone would have to really upset me this afternoon for me to turn around and make it virtual. So for the most part, bet on it being real, bet on it being right, and then all it really comes down to is just figuring out the numbers. That's why there's a part. God, that is inexcusable. That's why part of me thinks that for the appetizers, I'm going to put some weird type of lens or mirror where you're going to get a virtual. And that would appease me. I don't know, for some reason. It's not like I'm sitting my hand or anything, I haven't made the test up, but I'm really thinking about doing a lens or mirror appetizer. I don't know why. Yeah. 51 centimeters is the distance given on the front. Yeah, it is a given distance because it spaced it out, and there was a little arrow line saying 51 centimeters. It was not to scale. Some people got very upset with the fact that it was not to scale. I told them. All right. Any other questions? All right. So the appetizers for the final?
Yes.
Ooh, all right. So this is going to be the final from last summer. Appetizer 1 is you have unpolarized light going through a vertically polarizing filter. There is now an angle. The final intensity is 26.66% of I naught. What's the angle? For unpolarized light, it's I naught over 2. That's the light intensity in the middle. But we don't need anything about that because we've got I2 is equal to I1 cosine squared theta. This makes it I2 equals I naught over 2 cosine squared theta. Now, I final is I2. So if you have I2 over I naught, that is 0.2666 of, hold on, times cosine squared theta over 2. Oh, hold on. I'm an idiot. Wait. So I naught comes down. That ratio here is equal to 0.2666, and that is equal to cosine squared theta over 2. This becomes 2 times 0.2666 is equal to cosine squared theta. Square root of 2 times 0.2666 is equal to cosine theta, and then inverse cosine of the square root of 2 times 0.2666 is equal to theta, which gives us I don't know why I picked that number. 43.1 degrees. And that is the first appetizer. Is it what? Yeah. In something like this, all the problems have been either given two polarizing filters, give the angle, give the final intensity, give the initial intensity, stuff like that. Now, in the second appetizer, you charge an initially uncharged RC circuit. It takes 5 seconds to hit 70.5% of its maximum charge. And the capacitor is that. What is the resistance of the capacitor? So we have a charging capacitor . And you can interchange, and we've talked about this before, you can interchange the V's with Q's. Mostly because you know the relationship Q is equal to CV. The C's cancel and you can make that change. So this becomes Q over QM is equal to 1 minus e to the negative t over tau. In this part, I'm not going to do the numeric substitution until I get to the point that I want to do. That tau is equal to RC. So this becomes Q over QM minus 1 is equal to e to the negative t over RC. The next step is, ooh, and I missed a minus sign. So I'm going to take that minus sign, bring it over here, and then I'm going to have 1 minus Q over QM is equal to e negative t over RC. I'm going to take the natural log of both of these. And the one thing about natural logs is that they cancel exponential functions. So this becomes ln 1 minus q over qm negative t over RC. The whole goal of this is to find R. Solve for R. R equals negative t over c times the natural log of 1 minus q over qm. And I get that. Now it's time to plug and chug. The t is 5. The C is 512 nanofarads. Remember to change that into farads. Natural log of 1 minus. They say that at 5 seconds, the capacitor is at 70.5 of its maximum charge, which means this is 0.705. And that gives me eight mega ohms. 8 times 10 to the 6th. And it was, the answer is 7999496.7. So 8 mega ohms is what it was. All right, that is, those are the 2 appetizers for summer 214. For the spring 2016 214, let's get that going. Hold on, oh, hold on. I printed it twice. All right. So the 2 appetizers is this. You have a charge particle. It's an electron, and it is and I give you the mass and the charge, and it's moving at 300 meters per second in a 0.2 Tesla B field. And I ask for what's the period? How long does it take for this thing to make one rotation around? It's a circular motion problem of a charged particle in a magnetic field. It's a really good problem. Because it's circular motion, the sum of the forces, which is equal to ma, which is equal to mv squared over r, it's a circular motion thing, is equal to qvb. Those cancel. And what I'm going to do is I'm going to solve, I think what I'm going to do is solve for v. V equals QRB over M. And one of the things that people complained about is, what's the radius of the circle? You didn't give us the circumference, you didn't give us the radius. This is really messed up. And then I looked at them and I said, my famous line, it's a correctly constructed problem. So let's think about it for a moment. The velocity is distance over time. What we're talking about is the distance is 1 circumference, or 2 pi r. The period is the time. So this, for velocity, is equal to that. QRB over M is equal to 2 pi r over t. My r's cancel, so the radius is not necessary. Solve for period. Period equals 2 pi m over q b. M comes up, t goes up, qb comes down. So this is 2 pi 9.1 times 10 to the negative 31 divided by 1.6. Now in this particular case, the negative signs don't really matter. We're trying to find magnitude. Just the time. 1.6 times 10 to the negative 19. B is 0. B is 0.2. And once again, what's really funny about this is it illustrates Dr. Eschenberg's 3 types of numbers. The first number is the number that I give you that you need. The second number is a number that I don't give you because you don't need it. And then the third number, the most evil of the numbers, are numbers that I give you that you don't need. The 300 meters per second is unnecessary. It gets thrown away naturally. So a lot of times what I do is I give you unnecessary numbers and watch to see if you're trying to plug it in. Just because then it just shows me that you haven't really ascended to being an alphabet super. You're still plugging and chugging. And that gives me so I get 1.79 times 10 to the negative 10 seconds. Or you could say 17.9 nanoseconds. Huh? Oh, you want to see it? Okay. So while she's looking at that, appetizer 2, what we're doing is we're taking a look at 2 charges and figuring out the potential. Now some of you would look at this and go, I'm supposed to use vectors. This is going to take a long time. It's potential, not electric field. Potentials just add. So what we do is, first thing you want to do is you want to mark everything. 1, 2, 3, 1, 2, 3, 4, 5. So that's the point where we're studying. 3, 5. Charge 1 is at 6, -2. 4, 5, 6, 1, 2 is down there. And it is a positive microcoulomb. The other charge is at -2, -4. 1, 2, 1, 2, 3, 4. And it is a -5 microcoulomb charge. First thing you really want to do is you want to find those two distances. And really, that distance is the change in x squared plus the change in y squared square root. So for the first one, for charge 1, the 3 microcoulomb charge, the change in x was 3. In fact, it was 3 millimeters. I think we can get away with. Let's play it nice. 3 millimeters was the change, or 0.003 squared. The change in y, it went from -2 to +5, so 0.007 squared, and then you square root that. And that gives you a distance of 7.62 times 10 to the -3 millimeters, or 7.62 millimeters. For number 2, it went from -2 to +3, or 0.005 millimeters. The change in y went from -4 to 5, so 0.009 squared. And that gives you (1.03 times 10 to the -2 meters. So that is the distance for this. Now that we've got those, potential 1 is KQ over R1. So 9 times 10 to the 9th. Positive 3 times 10 to the -6. Divided by 7.62 times 10 to the -3. And I get, apparently back then I didn't care about numbers, positive 3.54 times 10 to the 6th volts. That's the potential for 1. The potential for 2, again, is KQ2 over R2. So 9 times 10 to the 9th. -5 times 10 to the -6. Remember, in E fields and in electric forces, when you're dealing with them, you always deal with magnitudes. With potential, the negative signs do come into play. Divided by 1.03 times 10 to the -2. and I get negative 4.37 times 10 to the 6th volts. And the total potential is V1 plus V2, or 3.54 minus 4.37 times 10 to the 6th, which gives me negative 8.3 times 10 to the 5th volts. And so that is the appetizer for 2. Appetizer 2 is a really good problem. Appetizer 1 is a really good problem. Appetizer 2, the other test I really like. The polarization, we've already done that, and I'm just not feeling it. So what does that mean? I don't know. I could be lying, or lying about lying. It happens. So that is, I've now satisfied your query. I've done all the appetizers for the final. Next question. Yes.
For this circuit analysis problem, is it going to be basically the same learning pattern?
Oh, I'm gonna change it. Don't think I'm gonna go uncreative. Not like, huh?
I was gonna say, could you go over that VA part again?
Of the VA from the test 1 that we had physically? Okay. Well, what we'll do, let's do this. What we'll do is problem 1. I've got these all turned around. I don't know which gate this one is. But it is this circuit problem. So I am, all the resistors are unknown, but I have to give you current, and I give you the potential of the battery. I need to know the resistance, and I need to know the potential at that point right there. The first thing I'm going to do is draw this circuit out and draw the circuit in its various swoosh diagrams. So the original diagram is like this. So all of the values are R at this particular stage. There are 2 squooshable parts of this circuit. That one, it's a simple series resistor. And this one, it's parallel. I'm going to call that one R1. And R1 is 2R. I'm going to call this one R2, and it is equal to 1 over R plus 1 over R plus 1 over R inverted, which makes it 3 over R inverted, or R over 3. So now I have this. I've got an R, I've got an R, I've got an R over 3, and I got a 2R. The one that I can immediately squoosh is this one. I will call this one R3, and it is 1 over R plus 1 over 2R inverted. 1 over R, make this 2 over 2R, so this is 3 over 2R. Or 2R over 3 is that particular block. Now I get this 2/3 R over 3, which makes the R equivalent two-thirds R plus R over 3, which makes the equivalent resistance 2R. Ohm's law, I is V over R, and this is the R equivalent. So I is equal to V over 2R, or R, the resistor value, is V over 2I, or that I naught. The V is 100. I is 20 milliamps, so 2 times 0.02. God, this is bad. I hate this drawing. I hate this Elmo. I hate this thing right here. I should throw it out the window when I'm done with it. So this gives me, forgive my atrocious handwriting, 100 divided by 2 times 0.02, 2,500. And that is the resistance of R, each of those resistors. And so that's how you do it. You still step through the squishing and find your equivalent resistance. And then you know Ohm's law, and then it just pops out on its own. I like this type of problem. It does, it does. The thing about this particular type of problem is that it's not about, it was never about the numbers, but you guys have to have your numbers. So what I do is just make a mockery of the whole thing and just set it up so that I don't have to worry about it, about the numbers working out, because they will. The part that we need to figure out is A. A is that guy right there. So what I'm gonna do for this Sudoku puzzle, I'm gonna have to find, I know what this part is. That's the high, or just V naught. What I'm gonna do is I'm gonna find that guy right there, or VB. Now, VB, if we go through these steps, that's where VB is, and that's where V naught is. I know the current going through the whole circuit. That's I naught. In fact, I naught is going through these three. Now, and so what I'm doing is I'm going to use V high minus V low over R is equal to I. I know the high, I know the current, I know the resistance. The resistance in this case is 2/3 times 2,500. So I'm going to look for V low. V high, V low, IR, V high minus IR is equal to V low. So 100 minus 0.02, 2/3, 2500. And so I get 66.7 volts. That's the potential at the low. Now that I know what the potential at the low is, I can figure out the current going through point A. The current is the V high 100 minus the V low 66.7 divided by the resistance of those two, which is 2 times R, or 5,000. And that gives me 6.67 times 10 to the negative 3 amps. That's the current flowing through that bottom rung. Now comes VA, because for VA, I was always trying to get to this point. To get to that point, I needed to know that one. Because what I needed to do was get the current going through that arm. And if I've got the current going through that arm, I can get to VA because I'll just drop it down from V naught. So VA is equal to V naught minus the I going through that lower part of the circuit times the resistance of that single resistor, R. So this is 100 minus 6.67 times 10 to the negative 3. The resistance is 1R, or 2500. And I get a potential of 83.3 whatever volts. And so that is how you solve for it. Yes? Yes?
So where did you get, where you found V low, where did you get
The 2/3, oh, what I had to do was I had to get to this point of the squishing. So you can treat those 3 resistors as a single resistor to get to VB. A resistor that is 2/3 R, because we stepped through this circuit squishing so that these 3 resistors became those 2 resistors, which became one resistor, which has the equivalent resistance of 2/3 R. And that's how I did it. Yes? I think you can get, it's a coincidence. I think it is. I would, and in terms of circuitry, yeah, I think I'm going to make it a little bit more complex, where you're going to have to do a few more steps. However, I think I'll even kind of tip my hand as to what type of circuit it's going to be. I think it's going to be, you know, that one with the capacitors that it looks like just a whole series of diamonds of capacitors? Replace them with resistors and find the equivalent resistance. It's actually quite easy. Because the thing is that you've got you look initially at it and you go, this is insane. But what you notice is that each of their 4 major diamond blocks, do you have it? You might. There are 4 major diamond blocks. So if you find the equivalent resistance of that one diamond block, it's just 2 sets of those diamond blocks in parallel. And so if you got it to a position where it looked like, if I said, give me the equivalent resistance of this, all the resistors are equal, you would laugh at me. This is easy. It's that one. This is the one. Now, granted, there's a tutorial on this, but it's with capacitor. You do the same thing but with resistors. What I would do here, they're identical. All capacitor ovals are identical. So what I would do is I would focus on getting the effective resistance of one of those ovals. And then that problem simplifies to that. Now, as to where the point's going to be, I don't know. You got to give me something. But it's something where I don't know what to do with that. But that's an idea that I've been kicking around. When I initially came up with that problem, the class just lost its ever-loving mind. And they said it was impossible. And I actually, for every time a student says that's impossible, I gain a year of life. So hopefully I will live for a very long time, because I've been told that repeatedly. So look at that and play with it in terms of resistors. Because if you look at just a block, you add those two and you add those two, and then it's those 3 in parallel. Done. So it's something like that. Now, as for what am I going to do with the points? I don't know. I'm going to have to make it a little bit more interesting. I'm going to have to figure something out. I'll have to make a subtle change. But the core of this is actually, it's quite simple. Just don't panic. Understand when I'm writing these problems, I am not here. Well, granted, I am here to prove how smart I am. But the next thing is I'm trying not to fail you intentionally. I'm trying to give you realistic situations where you should have been trained to deal with this. And so hold firm and focus on that. So did that answer the question? Oh, we got sidelined. Okay, good. Next, who's got another question? Yes.
Can you give an example of what like possibly
A random question from test 2. I do know, and understand this, I take that into account. Yesterday's test was me saying, I'm sorry, we're moving fast, so let me give you something that we've already covered. Because it's all about, it may be B field addition, just a simple B field addition. We did, what did we do on test 2? Was it that, who's got a test 2? I've talked about it, I've done it in class. Problem 3 looks eerily like you've got 2 wires. Find it. That's it. I'm going to keep 45. So if you've got if you've got two wires, that one will produce a B field that is like this. I want this one will produce a B field. Oh no, I don't want you. I want you. This one will produce a B field like this. And this one, what typically happens is I make one of the currents the bully. And so this one would have like 8 amps of current. This one would have 1 amp of current. And the talk or the question is, well, where is it 0? Where could it be 0? It's definitely not here because both of the B fields are out of the page. It's also not down here because this one is the stronger current. So at any point below here, the B field from the lower, stronger current is going to be greater than the B field coming from this guy. Always. And so there's no sense in looking down here. So what you do is you set it, you look for that distance X next to the weaker of the currents and set up your B fields and get it to work out. And it's really, I mean, it's pretty straightforward, but and it's been done. Check your notes. This problem's been done. Yes?
Okay, I don't know why I can't still think it's right, but when I worked on the course for number 3 on that test, how do you know it's going to the left and not the right?
Well, I know that the velocity is to the left because the diagram says so. And what you have to do is you have to, what I believe happened was that the magnetic field is coming out of the page. That I added it up so that the B field at, hold on, it would help. I'm pointing to the paper and I'm like, maybe it helps if I did this. When you add up the B fields at that point, you find out that it's positive. Because this one is producing a B field that is going into the page, and this one is producing a B field that is out of the page. And what you find out is that the B field from that guy is producing a bigger B field than the B field from this guy. So in the end, it's got to be a positive B field. So you do the right hand rule and you go V is that way, B is out of the page, so force is, so the magnetic force is up the page or upwards. And so that's how you can tell. You got to get the B, you got to figure out the value of the B field first. And then once you've got that, then everything else just kind of snaps into place.
I thought the FB was like, you know, in class one day when we drove around how velocity is to the left, and then FB is just opposite, but it should be opposite that first. And then force.
I think you're confusing this with magnetic induction on a bar. There's no bar.
Yeah.
Where's the bar?
There's not.
There's not. Alright, and so that's it. Here's how it goes. When I write a test, there's typically 4 appetizers and 8 to 10 problems. And then it's a lot like a garden. It starts growing. And then some of them will grow and they'll call an R. And then I go, I don't like that one, and just toss it out. And eventually I get down to 6 problems, 2 out of original building was somewhere. So I've kind of tipped my hand on a few of them already. So I think I'm allowed one problem where I can express myself. I have to have one. Which one? I don't know. Don't let other people look at it. Yeah, he told us that. He told us that. I understand you're 214, you've been here for just 4 weeks. Time to get out. And so let's just. I mean, it's amazing. Like in the fall, test 3 is the Thursday before, or I'm sorry, the Thursday or Friday before Thanksgiving. And then like 2 weeks later is the final. This is 48 hours after the third test. That's I mean, it's not going to be painful. I really intend on everybody staying here for the plan is 220 starts from is what I expect. The bulk of the class to start moving about 220. There will be a few who are just insane right next. Though I will say there was one student, this is how vicious I get. He was a perfect student. He actually should have been a reading child was very much. And I'm sitting there, he had hundreds on every day. And I go, look, he's gonna get an A. I accept this. But what I'm gonna do is I'm gonna keep that dude in this room for 3 hours. He's going to sit there. And what I did is I wrote the entire test in English. No numbers. I wrote out the numbers in English. And that dude stayed. And what was funny is that the kids were looking around going, that dude's been here the whole time. What are you doing? And I'm like, man, I wrote that test to beat him. You said 100 on it, but I made him stay. Because he was the dude who was like, I hand out the test and 20 minutes later he walks out. I'm like, dude, that's not happening all the time. Me and him are going to come to an understanding. So, true to my word. Yes. So any other questions? What time is it? 11:20? If we can make it like another 10 minutes. Yes. Excellent. So for this moving bar, so the B field, the externally applied B field, is in this direction, and let's make it unique. Do you want the external B field in or out? Pick. I pick? All right, fine. I'm gonna, okay, out. Bar left or right? Let's do left. The other thing I think has been posted on Blackboard are magnetic induction notes that go through every single permutation of this problem. And there are only 8 of them. No, 4? No, there are only 4, I think. So the B field is out, the bar is heading to the left. The question that I want to know is, what is the external force applied, and prove that the external force has to go left. So show that it has to go left, and I want to know the value of that. The area is this, and Faraday's law says that the electromotive force, and I'm only going to deal with magnitudes at the moment, is d phi b dt. Ooh, this may get better. So this becomes b dA dt. Now area is length times width. So I got to give you a length. Let's say the length is 2 meters. I'll even be nice. I'll say that the B field is out with a magnitude of 2 Tesla. I'm a giver. I'm not mean. It's not a necessary value, but I'll give it to you. The velocity is moving at 10 meters per second. So we've got all that set up. The current, which is electromotive force over R, means that the I is B over R dA dt. And I've kind of played with this in a little bit of a weird way. Area is Lx. So this becomes this. Fine, we're using a little bit of differentiation or Cal 1, but you gotta have it. You gotta do something with it. So B over R L dx dt is current, and dx dt is just velocity. So this is BLV over R. So the current, let's get the value of the current. The B field, oh wait, we do know the B field. I do have to give it to you. 2, L is 2, V is 10. Resistance, I gotta make this current, I'll make it 20 ohms. So it's 2 amps is the current going through that bar. Now, question is the current going clockwise or counterclockwise? The B field is out, which means that the magnetic flux is out of the page. Now, remember what we talked about in terms of stuff going in or out of the page, increasing, decreasing, stuff like that. If the bar is closing the area, if the area is decreasing, the change in magnetic flux has to be into the page, because the amount of magnetic flux going through is decreasing. If the bar was getting wider, the change in magnetic flux would be in the same direction as flux. Closing area, opposite. Opening area, parallel. Because the change in flux with respect to time is into the page, Lenz's law takes over and says the induced magnetic flux has to be out of the page to balance it out. The only way that you can get a magnetic flux out of the page is if you have a counterclockwise current. This counterclockwise current, when thinking only about the region of the bar, is from bottom to top. The force on the bar is ILB, which means that the force on the bar is I or 2, L is 2, and B, which is 2. So the force on the bar is 8 newtons. The direction of, or the force on the bar, that force direction is, if we're just using this as a way to remember just the direction of the force. Technically it's not correct, but we're not in Cal-based physics. I is this way, B field is out of the page. This is how we're going to use the right-hand rule in the test. So it points right. So the magnetic force points to the right. Summing the forces, which is equal to MA. The whole requirement of this bar is that we're going to make the velocity constant. For the velocity to be constant, the acceleration is 0, which means that we have a negative external force, it's heading to the left, plus the magnetic force, which is heading to the right. So the external force is equal to the magnetic force, which is equal to 8 newtons. And it's heading to the left to balance out the magnetic force heading to the right. And so that's it. Now there could be variables, other variables that I ask for, other than looking for the main force. I can ask for the current, I can ask for the resistance, I can ask for the velocity of the bar, stuff like that. So this also goes into the whole point of being able to understand what is it? The whole thing with alphabet soup notation. All right. So we've gone over. Let's take a look at. Let's review this whole thing. All right. E-field vector addition. What I'm going to do is this afternoon I'll publish the solution for that, and I'll write it nicely. Circuit analysis we've covered, magnetic induction we've covered, compound lens we've covered. We've gone over test 2 stuff that could happen, the wild cards. Test 3 material, understand thin films, single double slit, stuff like that. Probably pay attention to the stuff that was done in problem set 8 is what I would look at. And that'd be a good hint for what's in that. Yes? Diffraction grading will only be in the multiple choice, if it is at all. Diffraction grading will not be one of the problems. Mostly because single slit and double slit are way more interesting. All right. Anybody got anything else to talk about in terms of the final? All right.
Just the multiple choice from the past test, right?
Yeah, I'll make sure it's like that. I may basically just take test 1, 2, and 3 and then just physically cut it out of the test and put it in together. And then that'll be it. Because it's like the last day of school. The students don't care, the teacher doesn't care, let's just get out. All right, that's it. Study hard. See you tomorrow in Lamar. It is not in here and it is not in Lewis. It is in Lamar. The room number is in the notes that was posted on the blackboard for at noon. Yeah, noon to 3. SDS students need to show up at my office to 11:30.
How much time do you have this afternoon before you're going to start writing the final?
I'm gonna hold on.